Okay, so the second speaker of the seminar is Nikolai Leonenko, and he will talk about Dickman-type stochastic processes and non-local operands.
Okay, thank you very much for invitation. And again, the title of the program is anomalous diffusion. And I would, of course, it's a very large topic, and I would like to present my own view on the subject in which we are, in framework of which we will consider today's talk. So basically, well, one of the model of anomalous diffusion is the following. So suppose that we have a kind of Markov process, kind of Markovian evolution, whatever process. And basically suppose that we have an equation with derivative in time of u of tx. Let's say it's like transition density of Markovian process, and on the right hand side there is some sort of operator A. And basically, okay, we can also consider some sort of initial condition. And then it's well known that, well, you can imagine that A is a generator of Markovian process, and then u of tx is simply expectation with respect to x, f of xt, roughly speaking. But now that's a kind of well, it could be diffusion if you like, if you properly choose I. It may be second order operator, maybe something more complicated. But now let us replace the first derivative into something which we will call fractional derivative. I will denote this fractional derivative on this type. And basically, you consider the same problem with the same operator. And well, what is a fractional derivative? Well, I mean, we will consider fractional derivative of the following type. So basically, there is some function phi of t for which we consider fractional derivative. And then here there is one of the form of this derivative is the following: 1 over t. Here there is kind of kernel chi of t minus s, and here is, well, phi prime of s ds. That's for instance, if k of ts is 1 over gamma of 1 minus alpha t minus s to the power alpha, this fractional derivative is known as Caputo fractional derivative, which is probably the most popular in applications. And again, now the derivative depends on the kernel k. So what kind of kernel are interesting to consider? So basically, we have to consider Levy subordinator as small means parameter of the Laplace transform, and as big is stochastic process subordinator, Levy subordinator. And suppose that its Laplace exponent is phi of s. It is well known that phi of s has a Levy-Kingin representation. Well, I ignore some linear term here, which is, we assume for simplicity to be 0, and then we have integral from 0 to infinity 1 minus e to the power minus s x mu dx. Mu dx is, of course, Levy measure with some specific properties. And basically, this kernel k is nothing else as tail of Levy measure. So if you consider here interval from x to infinity and then Levy measure of this interval, tail of this interval, that's exactly the function k which appeared here. For example, if phi of s is equal to s to the power alpha, then kernel is coincide with the kernel of Caputo derivative. So this is probably the most popular in applications case. But what is more important, that actually we can now consider inverse subordinator. So we introduce here E of t, which is infimum of u such that S at U larger than T. Basically, it's a process inverse to subordinator. Subordinator is increasing its probability one Levy process. And basically, then the solution of this fractional diffusion problem, the solution of this problem with this type derivative instead of derivative in time, is given in very similar way to this solution. And the only things we have to replace now time into inverse subordinator. So basically, this is the same expectation with respect to x, f of x, but instead of t, we have to write down inverse subordinator, which is independent of Markov process x of t. So if you know the solution of problems for Markovian case with some operator, it could be generator, it could be some sort of operator which define Poisson process, maybe not necessarily diffusion, maybe point process, but to the end, the main role plays inverse subordinator. So basically, we have to replace time into inverse subordinator, and that's a fractional diffusion, anomalous diffusion model, at least one of the view on the fractional diffusion. Also, distribution is related to, u of tx is equal to integral from 0 to infinity. Here we have to put function u, which is of xs, and here is nothing else but density of inverse subordinator. So it means that the main role to go from the diffusion to anomalous diffusion, at least in this model 1, is to be able to study, to replace derivative in time into some sort of convolution time derivative or fractional derivative, which is in most cases, important for application is simply Caputo derivative. And then many problems can be solved in this way. It is very general view on the problem. Again, the key place is inverse subordinator, and density of inverse subordinator. We need proper to know density of inverse subordinator. So, what is a topic for today's talk? Basically, if you consider the most important case for applications and most case which is already studied is a case of Caputo fractional derivative, just this case. In this case, Levy measure of stable subordinator with Laplace exponent s to the power alpha, it is well known that Levy measure is equal to some sort of constant over x to the power 1 plus alpha. And the question is, what is going on when alpha goes to 0? Of course, we need to truncate this Levy measure because otherwise it's not Levy measure. And that's what we will call in the future Dickman distribution and related Dickman-Caputo derivative. And all these problems will be related to this case. So basically, Dickman distribution is a distribution of kind of relative to the most widely used in applications Caputo derivative. But in the case that alpha goes to 0, well, we will see that we need to truncate this, otherwise just to have a Levy measure. Okay, now let me go to my slides so that is why the title is Dickman-type stochastic processes and non-local operators. Under the non-local operators, I understood such derivatives because of they are non-local, in contrast to ordinary derivatives d over dx. And under Dickman-type stochastic process, I will understood all this stuff related to the Dickman distribution when, as I said, we assume that alpha is 0 in a sense. Okay, I will describe this later. Okay, so structure of the presentation. So first of all, I will advertise a little bit so-called Dickman distribution, why it's important. And this is, then I will discuss OU type processes, Einstein-Lubeck type processes, a generalized Dickman marginal distribution. This is joint project with Grahovas, my former PhD student from Croatia, Kovtun, my present PhD student and second collaborator of Kovtun Peleshev. Then I will discuss the processes with long range dependence, superposition of Dickman type processes, and related limit theorems. Then I will go to the inverse Dickman subordinator. As I said, this object plays critical role in the construction of anomalous diffusion related to Dickman distribution. And after that, we'll discuss fractional Dickman-Poisson process. The case when this operator is simply an operator which defines Poisson process in classical sense, difference operator. But of course, there are many other possibilities here, and we can consider second order operator, like consider Brownian, Dickman, motion, whatever. Okay, so and the second part is a joint work with my Indian colleagues Gupta Kumar and my Brazilian colleagues Jaime Vaz from Unicamp Campinas. So it's kind of two type of processes. Sorry. How to go back? Okay. As I said, Dickman distribution. So basically, we consider generalized Dickman random variables. This is so-called D. We denote D theta, which has the following Laplace transform. So you can see that this is nothing else but Levi-Hinchen representation. Where is here? But now Levi measure new D, well, dx, but now it's du, is simply du over u and indicator because of now integral from 0 to 1. That's truncation. Basically, Levi measure is of this form, theta over u indicator of a set 0, 1 du. Of course, this distribution has a finite moments, expectation, variance in this notation. And the question is, what is the density of this distribution? It turns out that's not a simple question, because of, in spite of very simple form of Laplace transform, of course, truncation gives you a very difficult problem of inversion, because of usually nice we have nice functional full space or half of a space to invert, not this type. But however, one can find that the density of the Dickman distribution is given by this elegant but quite complicated form, because of here there is some function k, which are, is kind of infinite, such a complicated integrals, and gamma is earlier constant, and basically these sets are very specific form, and well, I mean, there is also a recurrent relation for density. If x between 0 and 1, we have just this density, x to the power theta minus 1, and if x larger than 1, we have a relation between the density on the previous subintervals and when x equal 1. So again, if theta equal 1, which is most important maybe case for applications, I will tell you about this, we still have the density is a constant. So this density has a flats actually, which is very unusual for probability, but I will discuss this a bit later why.
And what is theta in mu?
Theta is just a parameter of...
e to the power minus theta.
Yes, theta over nu and truncated, that's a Levi measure. So it turns out that even density, existence of density has interesting mathematical history, and I will tell a little bit about this history. Basically, this function, Dickman function, appeared with relation to the number theory. Suppose that k is integer. Okay, k is integer. And we denote P1 of k is the largest prime divisor of k. Largest prime will divide by k, so largest prime. And actually, if psi n is a uniform random variable on the sets, discrete uniform distribution of the sets from 1 to n, then basically probability that rho 1 of psi, well, psi n, let's say, in this notation, less than n to the power 1 over a, in this case, theta is equal to 1, corresponding to this notation, goes to the rho 1 of a, which is known as Dickman function. And Dickman function satisfies the following relation: x rho prime of x plus rho of x minus 1 is equal to 0 if x larger than 1, and rho of x is equal to 1 when x between 0 and 1. So this is basically, well, we can construct here some sort of CDF, PDF from this relation, but again, this Dickman function appeared in the number theory, and it was the original paper by Dickman, which was written in about 100 years ago, and it's an interesting history. I will not go to describe this interesting historical fact, but again, you can see here on the slide this function if theta equal 1. If theta equal 1, rho of x is 1, as you see. And basically, this is more, if theta is not 1, we have a more general differential difference equation, which first arrived in context of the number theory. And actually, it's continuous. Maybe half of the papers, or maybe more than half, are in number theory, not in probability about this Dickman, well, different distribution, of course, because we have random uniform distribution. So basically, interesting that, well, it was forgotten by probabilities, but now it's recovered as a new important distribution. I will advertise this even in the future, but interesting is after that, people discovered that in Ramanujan's unpublished paper, there is also Dickman function, Dickman distribution, so they are now published, and actually probably Ramanujan was the first who understand the importance of this function and this related distributions. But anyway, I'm not going now. History is interesting, but okay, let's go further. But anyway, our density function of a Dickman distribution is given in this form. So basically, its support is positive numbers, and there is a Dickman function which appeared in the context of number theory, and also e to the power minus gamma theta, which is normalizing factor. That's easy to imagine what we are talking about. So basically, that's a possible, well, actually this Dickman density function could be very different, as you see from these pictures, and again, it could be like this, it could be like this or like this, but also it's possible, as we know, that it could be could have some flat, well, very unusual for densities, but actually, again, it's possible for this possible different type of densities of Dickman-type, Dickman densities.
And is this parameter theta, is theta the same as in the Poisson-Dirichlet distribution?
Yes, I will thank you. So actually, this distribution after that appeared under different names in the paper of history is very exciting, but again, this is in other papers on population dynamics. This distribution was called by I think Dirichlet-Poisson distribution, and also in some other on Grant combinatorics is what called by I think Goncharov distribution. So there are many names of this, but I use just most modern Dickman distribution. But you're right, that's exactly the same distribution, and it appeared under different names in different circumstances.
So that, if I remember correctly, it's the maximum. It's the distribution of the maximum of this Poisson-Dirichlet.
Yes. I will a little bit relation to Poisson distribution will be a little bit later. So just a moment. So this is again some sort of facts about Dickman distribution. So we can appear this Dickman distribution if it's the limiting distribution in this scheme 1 over n k yn are independent random variables with Bernoulli distribution and parameter theta over k. So basically, you remember that theta over k is now theta depends on k. I mean, it's kind of related to what is known as Shibuya distribution. But anyway, and also there is a representation in this form. If you have sequence of independent, identically distributed, uniformly distributed random variables, we have a kind of representation of Dickman distribution in this form. So, kind of geometric progression, random if you like, or whatever. Okay, now it's a relation to the stochastic processes, in particular to the Poisson distribution. So this is not what is written in the paper by Yor and others, and I think Griffiths wrote papers about this. Of course, all references it's not published, but in archives there is all references. But now is a kind of interesting fact, at least for people from probability. So suppose that we have a simply Ornstein-Lebesgue process driven by Levy process. So if Levy process Z is just a Brownian motion, that's a process we teach our students usually in course of stochastic processes. And it's known that distribution effect of C, I mean marginal distribution of stationary process is a normal distribution, just a Gaussian distribution. However, well, we need some conditions on this Levy process, but it's kind of very common model Ornstein-Lebesgue process driven by Levy process. And this process is commonly referred to as backward drying Levy process, BDLP. And the question is to probabilistic audience, well, what is the next important process in probability after Brownian motion? Definitely Poisson process. What's going on when Z is Poisson process in this equation? What is the marginal or station distribution of this? And that's the first result, which is simply to prove, but for us it was surprising that it is new. Well, at least I think it's new, but that basically, if you consider as a driving process homogeneous Poisson process is parameter theta, and then actually the marginal distribution is Dickman distribution, exactly with this complicated density which was written before. Of course, covariance function is exponential here, and basically that's the first model in which stochastic process appeared with a Dickman distribution, and we call it OU process with Dickman distribution. Okay, so I will skip probably some details regarding the transition density because of it's important for simulation, but probably not important for exposition, since I would like to have more time for other things. So let me skip this. And well, again, so we have a stationary process with Dickman distribution with nice covariant structure. What kind of processes limiting distributions we can appear? Well, if we have just a U process, we know that this process is mixing. And of course, with mixings, we have all spectrum of limit theorems, and it's not difficult to prove that. Basically, we have here convergence to the Brownian motion, well, in uniform topology, for instance, and no problem when we have just this process. So I will see, you will see later a much more complicated limiting theorems.
It's continuous, right? It's Poisson-driven process.
Yes, but it's integrals as usual. You have some. I mean, of course, yes. I mean, you have to consider D for sums and C for sorry, thank you. And Schorhot space for sums and C for a continuous function. Okay, so that you're right. Yeah. Okay, now what is the superposition of OU processes? Well, I don't know. It's known how new this topic in this audience, but basically, okay, maybe for me here is important. So suppose again we have a dxt OU process driven by Levy noise, and plus d lambda of L of t, and basically we would like to consider psi as lambda as a random variable. Let's say with gamma distribution or any other positive distributions. And that's another way to consider anomalous diffusion or anomalous, well, jumps processes, because actually correlation function of a U process is given e to the power minus lambda t. But if you consider now, roughly speaking, lambda as a random, let's say, okay, psi pi d psi, of course we can obtain long range dependence from Tauberian results, and basically randomization of psi gives us anomalous. Well, diffusion maybe not a good word here, but anomalous process with anomalous behavior of variance at least, and probably new limit theorems. That's the idea of superpositions. But of course, it means that formally we have to consider here kind of, instead of Levy process, random measure, which has a Levy Hinge representation, and which depends both from random field measure, because of one parameter of this will randomize lambda, and another will randomize t. Well, it's not we have properly to write this object, and this random measure has Levi-Hinchian representation I z of A is equal to e to the power I, let's say m of A minus sigma square of A per plum. This is Gaussian case, and plus here integral which with Levi measure. And basically we have to consider random fields which with two parameters, and we can define these stochastic integrals in form of Rashpur-Roginski for those who know this topic. And basically that's how to randomize, practically how to randomize this equation, how to make lambda random, and what kind of object we can obtain. Okay, it's kind of technical, I will not go to details, but again, that's what we have here. So basically, consider A plus over A plus represents the randomization of lambda, and suppose that there is a probability measure pi on A plus, such that basically this measure is kind of factorized. I mean, we can independently randomize lambda and to consider a Levi process to have marginal distribution, because for any self-decomposable distribution, there's a formula how to define marginal distribution of these U processes. And again, basically this is Levi-Hinchian representation, which is represent Levi process here, L, and pi represents randomization of lambda. So basically we have to write decision to define this stochastic integral in some special sense. There are conditions when this integral exists with respect to infinitely divisible random measure, and to prove that it exists under some conditions. That's a kind of general. Of course, it's not here, I think, not so many details, but what I'm doing is clear. So k lambda of z is a Levi-Hinchian exponent for a lambda, for L of 1, and pi is randomized lambda, to make lambda random. And that's a definition, basically. The sub-U process, superposition of a U process is given by this formula, in which basically lambda of dxi ds is, as I said, a random field with infinitely divisible distribution. Independently scattered random measure, which function of two parameters. And again, that's a randomization of lambda, which is now psi here. That's a randomization of lambda. And basically, this integral is existing in form of as I said, there is an integration, Rashpur-Roginski integration special, and there is a necessary sufficient conditions when such an integral exists, when we have infinitely divisible random measure. And also there are some sufficient conditions which are very simple. Just we have to consider functions L1 and intersect with L2. So, but of course, there are, there are ways how to define these stochastic integrals. So that's a general sense, and now let us define a Dickman process with marginal distribution as we have such a k lambda of theta, and we will refer this process as sub-U process with which is defined by this object Dickman sub-U process. So basically, as I said, correlation function, which was a correlation function with exponential Markovian for a process, for a OU process, now became with some measure, and from this measure we can reach long-range dependence. Basically, we can reach that integral of correlation function will be equal to infinity. This effect is known as long memory, and there is a huge literature of this. So basically, we can reach both short and long memory playing with this measure pi, which randomized lambda. Okay, that's a I skipped some method of simulation which are based on the transition densities of this process, but anyway, that's a result of simulation which can be done by this formula. And again, for a sub-U process, when we have a weak dependence, short memory, integral of correlation function is finite, like this one. So in this case, the limiting process is Brownian motion, and we have considered normalizing factor, which is classical square root of t. And again, we consider here only finite dimensional distributions because of these topologies. There are some special questions which I'm not going to discuss, which kind of topology we have to choose here, not for this, but for other conversions. Again, this is general definition. What is the Bridget conjugate of slowly varying function? Probably most of you know this function, and again, assuming that pi has a slowly varying behavior, then that's a distribution function of pi. Pi is distribution of density of pi. Pi, you remember, represent randomization of lambda. Lambda has a distribution with positive support and such a density, basically. Of course, you can see here tau-varying result, abelian results via this parameterization. And basically, we obtain first non-trivial limit theorems because of actually now, you remember that for independent random variables, so for a weakly dependent random variables, when we have a second moment, stationary processes, the limiting distribution is just a normal or stable if there is no second moment. But here we have second moment, but limiting distribution is a stable. So it's the first result of unusual behavior of this type of integrals. So again, limiting distributions, even x of t has a second moment, and normalizing factor, of course, depends on alpha, which represent how we change this measure pi. If it's roughly speaking, if pi has a gamma distribution with some parameter alpha, then the limiting distribution is stable. And this effect, so basically you remember that for a long-range dependence for a non-linear Gaussian random processes, all the theorems, Taco and other people, in which they have non-Gaussian distribution for a long memory, but they have again moments. They have moments like Rosenblatt distribution and others. And this is something too. Basically, it means that such a specific non-Gaussian situation and long-range dependence gives you such a typical results, well, which is published actually. So I mean, this result not published, but more general results are published from which we can derive this result. So this is first unusual things. Another thing that actually, if you consider the so-called scaling functions, if you consider a moment of order v, log expectation of moments over log of y, you remember that y is a, here there is no y, or there is y is a integral. Oh, there is no y. Okay. Oh, yes, y is the integral. So, okay, there is in slide notation is missing. And then basically it means that if moments of the integrals of order y divided of log t has a limit, we call this function scaling function. And usually it exists on some intervals, and basically stochastic process is intermittent if there is a some at least 2 points, but actually it works for any points, that we have such a monotone behavior of this scaling function. This effect on intermittency is known in Anderson models, in many other models, but actually I would like to emphasize that in framework of randomized OU processes, with, we can again obtain such intermittency models. So. So it means that if we consider x star of t cumulative process of Dickman OU process, sub-OU process, not OU process, important that we only for a long-range dependence we have such an effect. Then basically the scaling functions can be computed and we can obtain intermittency in these models. Okay, this is scaling functions and which are clear seen and clear consistent with definition of intermittency. Well, now to go slowly to this what we called anomalous behavior of solution of some problems, because of our aim is basically to go to this new non-local operators. Again, we need to study properly inverse subordinator because of these key elements of the story. If this element is known, we know asymptotics, we know how to compute, we can compute on other things according to this general scheme. And that is why let me go to the so-called inverse Dickman subordinator. Basically, our aim is for this Dickman process to study process ET, how it is behaved. Okay, as you know, basically, this is so-called definition of Bernstein function. Probably this audience is known. Basically, this is the same as was before with Levi measure nu, but we have here linear term, which is not important for us now, and this is condition of Levi measure. That's a representation of Laplace exponent of any subordinator. So using the results of Caputo, Jabashan, Kauchubeito, Aldo, there are many people who work now in this area. We can basically define such an operator, as I said. And nu is nothing else but, well, there is here a, I assume that a equals 0 is my picture, but if a is not 0, we have to add here a, and basically that's exactly tail of a, where is the tail of a, yes, kernel k in this non-local operator is the tail of Levi measure. So that's exactly, I repeated what I already said. So nu bar of s is a tail, and we can here a tail. That's a generalized Caputo derivatives, if you like, for any Levi subordinator. And basically, we have too many non-local fractional integrals in the book of René Schilling and others. There is examples of all subordinator. I think number of examples 256 or something, but they're not. There's no Dickman subordinator in this list, so that's too many non-local integrals. However, that's exactly what we called now. Well, we can define Riemann-Liouville or regularized version, Caputo integral, and again, here nu is simply related to Dickman subordinator, and again, this is Laplace transform of Dickman subordinator, which is already was mentioned. We can represent this in form of the exponential integral. This exponential integral we can represent in this form, and basically we can, okay, that's exactly truncated Dickman subordinator once more. Here is a mistake. Should be here x, not x square. And sorry, and basically that's exactly what we already know, that for a Dickman distribution, we measure is theta over u in indicator. And of course, because of now we have a stochastic process, we need to introduce in density t. So this is again the version of these densities of a Dickman distribution, but now the function not only x but also t. Here is new element is t. If t equals 1, we obtain the densities which are already discussed. Basically, that's also cumulative distribution function of the Dickman subordinator. Okay, now how to get the density of a inverse process, because actually it's a first passage type problem. We have to solve completely first passage type problem of the Dickman subordinator, for a Dickman subordinator. In fact, there are formula how to relate. There are general formula, and for this general formula we can obtain. Let me maybe. Yes, we can obtain. Sorry, I will. Oh, no, it's not in the slides. But anyway, okay, let me go step by step. So basically, there are three forms of this density of inverse subordinator, because as I said, in all formula for anomalous diffusion, for anomalous Poisson process, we need the density of inverse subordinator, and this density is now, we have three forms of this density. It's quite technical formula. Maybe I will not explain in full details how we derive it, but what we have to understand that there are nice formula for a density of f of xt, which is the density of inverse subordinator, and well, written in some form. Well, I mean, many integrals, but we see the density itself is complicated, so inverse is also has a complicated form. And that's alternative form of a density is given in this form, again with some complicated but clear functions. I will show pictures a little bit later. And that's all. Basically, this formula is very similar to what you mentioned in the paper of Yor about Poisson distribution. There are some similarities in Yor and other people with this formula. And that's how it looks like. That's a density of function. And again, that's a Dickman which now depends on t as well. And that's a two-dimensional plot because we have x and t. And now it's the density of, well, I mean, as I said, to define this object, which is now generalization of a Caputo derivative, because of measure is truncated, alpha is equal to 0, and there is here truncation indicator. Basically, we have to find the tail of a Levi measure, which is integral of s to theta over u indicator of this function. This is minus theta logarithm s, or zeros. And basically, that's a caput of new fractional derivative related to the Dickman subordinator. So it means that if alpha is not 0, between 0 and 1, that's a Caputo derivative, and a Dickman derivative is given this form. Instead of power function, we have logarithm here, some sort of logarithm, which is typical for integration if you know integral from x to the power n, there is logarithm 1 over x and so on. And basically, we can define also Riemann-Liouville version of this Dickman, generalized Dickman fractional derivative or non-local operators, whatever you like. And that's a Laplace transform of this function. And again, you see that there are some explicit form of this. You have to invert, and basically the probability density function of that's still Dickman subordinator, sorry, is given by this satisfies this equation with in which here is Dickman fractional derivative, which was already introduced, and there is a moment indication. Basically now, now we arrive to the main problem: how to find the density of inverse Dickman subordinator. First passage time of the Dickman-Levy process. In the other words. Okay, so this is, well, quite technical. I will omit some details, but basically we have to consider Laplace transform in time, Laplace transform in x, and manipulate with this function. Of course, this process is non-Markovian, non-stationary. That is why, actually, I mean, for Markovian problem, we are going to non-Markovian, and this process is not Markovian, non-stationary, and that's anomalous diffusion if A is kind of generator of diffusion, if you like. But now we are going to concentrate on the Dickman case, and basically that's the densities of inverse Dickman subordinator given in this form. Sorry, formula complicated, but even density of different distribution is complicated. But well, we have to. But they are computable. I will show you that. Okay, that's elements of this formula, and that's a direct formula which is can be obtained direct computation. You see that. Actually, that's the correct formula for inverse Dickman subordinator, but we're trying to compute asymptotics or even just to realize on Maple. It's impossible to, I mean, for us it's impossible, maybe for somebody it's possible. That is why we developed another formula, as I said, and basically that's the densities which are, at least we can compute this density of inverse Dickman subordinator. You can see that for different t, different x, we can see this well, that's densities. Again, there are analytical form of this, there are computational form of this, so potentially we have some limit of this, and we can basically compute distribution of u of tx, anomalous diffusion, we can compute potentially using this formula, where u is a density, transition density of the Markovian diffusion. Okay, that's how it looks in 3D. Because of, as I said, there are three formulae. One is very complicated, and so others are possible to use in terms of asymptotics, in terms of computerization. That's the pictures. Well, again, now let me omit. Maybe we can compute actually Laplace transform of a moments in explicit form and asymptotics. That's asymptotics we need to know, because usually even for an inverse stable subordinator, the density of inverse subordinator is complicated, and basically we have only asymptotics of these to investigate this form. Only asymptotical behavior are possible for this form. And that's again simulation of Dickman left and inverse Dickman subordinator. Of course, inverse subordinator is simply inverse function to pass of the Dickman subordinator, but in probabilistic terms they are very different. Dickman process is independent increments, stationary increments, and Markovian, and in inverse Dickman is not Markovian, non-stationary increments, and so on. I mean, if their similarity are kind of not in terms of probabilistic properties. Okay, now again, we are in this scheme basically. What we built? We built a distribution of a Dickman. We built a distribution of a inverse Dickman subordinator. So ET is known. You see the pictures, 3 type of formula. So we know the solution of this now non-local problem with non-local operator in time is given by simply superposition of, we have instead of time to replace it into independent inverse Dickman subordinator. So that's our solution. And now we can think about what kind of operator we can choose instead of A. So if you choose second derivative, it will be Brownian Dickman motion, yes. But in these slides, we have chosen, and this is published already, just an operator corresponds to the Poisson process, classical Poisson process. What is going on when we consider superposition of a Poisson process N of t and Dickman subordinator or inverse Dickman subordinator. We can consider both models. And basically, there are equations for these 2 models, and that's exactly what people understand under the model 1 of anomalous diffusion. I mean, diffusion probably is a little bit not a proper words because of its operator could be related to other stochastic processes, Poisson process, maybe non-homogeneous Poisson process, okay, Brownian motion, maybe Pearson diffusions, whatever. But in fact, now we have all components to develop many type of theories. And in this case, we consider simply the first object is instead of time we introduce Dickman subordinator. So that's characteristic functions. That's a moments covariance function. We can find covariance function and Levy density of this process because of Dickman is Levy process, Poisson process is Levy process, so superposition is Levy process. So we have still Levy process when we use Dickman subordinator, not inverse Dickman subordinator. So that's a Levy density we can compute explicitly. But again, most interesting is fractional time fractional Poisson-Dickman stochastic process. In this case, we have N of t is a standard Poisson process, homogeneous Poisson process with parameter lambda. And instead of time, we substitute independent inverse Dickman subordinator. So it means that if we substitute instead of inverse Dickman subordinator, inverse stable subordinator, then we have an object which is now well known under the name of fractional Poisson process. But this is kind of new process in a sense because of we replaced stable subordinator into inverse into Dickman subordinator. So that's our object. Okay, they're independent. We can compute, of course, local probabilities, state probabilities, because of state probability is given by this formula. Now this is Poisson distribution, and this is density of inverse Dickman subordinator, and we know that we have 3 formula for the density. So that is why actually we have state probabilities. Well, we have an equation. You can recognize in the right-hand side Poisson equation, which we teach in our courses for students, minus lambda pn minus lambda n minus 1, this initial condition. And in the right-hand side, we have a non-local operator, which is determined by Dickman subordinator. So if, for instance, this is we replace this non-local operator into Caputo derivative, that's what people called this process fractional Poisson process. So again, we have a new representation of this process. We have some information about waiting times, T1, Tn. And in this case, again, waiting times, you remember that for a Poisson, classical Poisson process, waiting times are exponential. If we replaced dt into Caputo derivative, this waiting time between events have a Mittag-Laffer distribution, heavy-tailed Mittag-Laffer distribution. But for our case, when we are going further, we replace now this local operator into Dickman Caputo derivative in our terminology. We obtain that waiting time have such a Laplace transform. Again, you remember that h of yt is the density of inverse subordinator. I mean, that's the same as h of at. It's not consistent with my is my node. And basically we built new point process called Dickman-Poisson process, for which we have, well, I mean, of course, the definition could be by superposition, because in non-Markovian case, we could not consider equations as definition of the process. This is only for Markovian case. So our process is proper definition is via superposition, as I said. So we have a Poisson process, independent inverse Dickman subordinated. That's the definition. Both processes are well defined, so the resulting process is well defined. But margin distribution of this process, okay, we have a state probabilities. We have a but margin distribution satisfies this equation. So basically, it's a probabilistic solution of this non-local equation. So we could not start as usual with equations because of its non-Markovian case. So, but anyway, you can recognize here well-known equations which you know from our students' time. And again, you have a renewal representation, but waiting time are very different from an exponential, very different from a Poisson case. For a Mitter-Klaffler case, well, not very different from Mitter-Klaffler, they are related to Mitter-Klaffler, but however, given explicitly in form of Laplace transform. And basically, the question is, what is the dependent structure of this process? So we can compute covariance function of this new Poisson process. Of course, it's not a minimum between T and S anymore. It's a quite complicated expression, and here for a fixed S, you have a long-range dependence. For a fixed T, we have a long-range dependence. So it's a non-stationary covariance function of long memory type, and U here is what is known as renewal function, basically. Again, the key place is expectation of inverse Dickman subordinator, and again, the key place here is the density of inverse Dickman subordinator. So as I said, this three formula I took so many times with them because of their key formula for everything. Inverse process plays important role in this picture everywhere, for a renewal representation, for a covariance structure, for whatever. Well, actually we can formulate martingale property. So, well, we know that Poisson process minus lambda t is martingale. That's exercise for students. Similarly, here new process minus inverse subordinator instead of t. It's martingale with respect to proper filtration. And again, let me emphasize this in this statement. There is not only a martingale property to one side that we have, but in another side, it's a so-called Watanabe characterization of a Poisson process. Probably in this audience, you know that if you have a Poisson process minus lambda t is martingale. This is obvious. But if you consider point process without double points and it is martingale, then it's a Poisson process. This is non-trivial part of the statement called Watanabe characterization of a Poisson process. So which is absolutely non-clear how to get Poisson distribution for martingale property. Well, again, I'm not going to detail, but here is the same story. So basically, here is if and only if. So it means that if there is an inverse Dickman subordinator such that m of t minus lambda of t is martingale, then m of t is a Poisson Dickman-Poisson process, which is superposition of Poisson process inverse Dickman subordinator. So again, this is not only a statement to one side, but statement in another side as well.
But ET is a random process. What is the filtration? In Watanabe's theorem, lambda t is a deterministic function.
Yes, but this is now a stochastic process, and filtration is here.
Ah, it's
minimal sigma algebra.
Yes, these two, which determine inverse and this one. So, okay, this is not trivial things, but again, so my time is over. But
5 minutes late.
5 minutes, yes. Okay, so we are continuing this type of consideration, and again, we have built a generalization of a classical Poisson process via Dickman subordination, and we use different constructions, and so far we are discussing a martingale property. So if process MT such that m of t minus lambda ed of t inverse Dickman subordinator for some subordinate is martingale, then under this filtration, in filtration there is a inverse process as well. Then m of t is a Dickman Poisson-Dickman process, fractional Dickman-Poisson process, or non-local Poisson process generated by Dickman subordinator. And there is a covariance structure. Of course, we can investigate again. Again, the key place here is density of linear subordinated, because from this formula we can potentially investigate and to prove long-range dependence of this covariance function, which is, if you start with computations, is complicated but doable. We did it. Actually, this paper, the last part of this paper is, the first part is not published, only submitted, but this part is published, so I can give a reference. Of course, after that we can go further because of we can, for instance, consider, let's say, compound Poisson-Dickman processes, replacing Poisson process in the classical model into Dickman-Poisson process, and E of t is Dickman. So superposition of a Poisson process inverse Dickman subordinator. And for us, it is interesting to consider the case when jumps are discrete distributions. So basically, of course, jumps could be continuous, but most people like exponential, but we consider jumps probability that xg is equal to j, j is 1 over k. So, and then basically, this is so-called case order Poisson process. It means that if you consider the classical Poisson process, just if n of t is just a Poisson process, classical Poisson process, then xg has discrete distribution. It means that in these equations, which are writing in difference equation, we can consider not only on two terms, the first and the second, pg and pg minus 1, but case term. We can consider case term of, it's a case term difference equation. That's basically model. So basically, fractional Poisson process is a process with such a process. And basically, we can study now such a time change Dickman processes. And again, this is case time Poisson process. Case time means that if you consider the state probabilities, we consider not only lambda minus lambda pn plus lambda pn minus 1, but also plus and case terms here. That's exactly the same as written here. And what else? Well, there are several models of this which are probably I would be able to, I think I explained what I would like to tell you, and of course there are now many ways to develop in to replace the A into second order operator to consider the Brownian motion in study asymptotics. We can consider more general diffusion processes. We can well, with generator A, we can do many things, and actually we can consider kind of risk processes for insurance with this new Poisson process and so on. I probably will show on the literature, and that's it. I mean, because of, let me skip the details because of its a simulation. Also, there is a non-homogeneous version of this, but again, so, okay. Okay, so I mentioned many results which I obtained in collaboration with other people, and not only with these people we have mentioned in the beginning. So basically, Giacomo Aletti and Elie Merzbach are co-authors of the paper with martingale characterization. That's the main facts about Watanabe characterization in this paper. So this is Bartner Simpson, his collaborator related to this SAPU processes, of course, because of its also Murat Taku and Daniel Grachwasa, collaborator of this paper in which we obtained the general form of intermittency limit theorems, which we mentioned here as partial cases. And scaling function also are obtained in collaboration of Murat Taku and Grachovac from Croatia. And one more paper. So basically I mentioned this paper also. So what else? Okay, that's a paper which is, okay, it is not, now it's published. It's only some sort of online published. Now it's published completely. And there are some other papers, particularly in Meerschart, Mark Meerschart, we obtained this form of covariance function, and Alla Sikorsky, and some related paper of beginner Singer related fractional Poisson process, and so on. So what else? That's all. Oh, we still have more. Oh, it's all. Yes, I mean there are some other related papers by Kochubi in which he considered introduced such a relation between subordinators and these kernels. Also, Maynardi and Fluscalis, the first paper about fractional Poisson process published in the Italian Journal of Mathematics. It's an interesting history of this. Then I mentioned the classical paper about fractional Poisson process by Meir, Shartan, and Sabi. Molchanov and Panov about Dickman, they call Dickman-Goncharov distribution, and also Penrose White with application of the Dickman distribution to random graph theory. And that's an unpublished paper on Ramanujan in which he obtained such an equations, and probably that's more or less all. Or there are some others. No, it's all. Okay, thank you very much for your attention. I think I'm exactly in time.
Questions?
Is there any functional version of the result from number theory you mentioned, in which the limiting process is the process with Dickman marginals?
Yes, this line of research, which was first mentioned by Ramanujan, but basically we know this from the paper of Dickman, which was among literature, has a long continuation. In the paper, we published several papers. It's a long story. We have found how many? 20 or 25 different papers, with including functional. So this line of research with number theory, it's still one of the main line of research in number theory. And there is asymptotics of this function. I can give you references, but, well, I mean, the answer is yes, but it's not trivial, like you can formulate in a couple of words. That's a huge branch of research. So also in number combinatorics, if you consider random combinatorics, also Dickman distribution describe limiting behavior of the permutations, random permutations. That's called Goncharov. Why is it called Goncharov? Also in random graphs, here is a paper of White and Andrew White is one of the organizer, and he is here or not? No, Andrew White is here.
He's not here.
Not here, but anyway. So he also obtained in the random graph theory. So today was mentioned already, so-called special type of graph, and Dickman distribution appeared in spanning tree. So if you, because of its random geometrical progression, and for a graph, it's very natural construction, and it appeared as a limiting distribution. That's a paper by Penrose and White. In many others. But again, regarding your questions, I simply can give you some, even in my computer there are, if you like, I can send you some papers. It's a long story. There are asymptotics, there is a, as you say, functional version, everything. There is, but of course it's another branch of research.
You have Watanabe-type theorems for inverse subordinators. Is it general result, or is it only for Dickman's?
It's general. It's general. As I said, there is a paper of Elie Merzbach from Israel, and myself, and Giacomo Aletti from Italy, in which this is described all conditions. It's very general, but of course it's not trivial as well. I mean, one size is trivial and another size is not trivial. It's published 5 years ago, 4 years ago.
No more questions. Let's be
Okay.